an acid will neutralize a base, turn the base into an ion. The base will be in the water. So suppose you have an acid that's all in a water solution. You have your oil in your water. If it's an acid, if you have an acid, you have a whole bunch of things in there. What you do is you turn it ionic. Make it basic. Make it basic. If you make it basic, the acid will turn into an ion. The acid will remain in the water. Okay, the acid will remain in the water. But the base, the organic solvent, the organic part, will have the base. Okay, so you will separate it. If again, you have a water solution, you're making it basic. The acid will be in the water part. Okay, the acid will be in the water part. The base will remain in the organic phase. Okay, so let's try this again. We have it in water. We are turning it basic. Acid turns to an ion. Acid will be in the water phase. When it's an ion, it turns into the water. Right? That's where it'll be. Right here. Suppose you have other things in there. You have a base in the water solution. You add acid. Make it acidic. The base will turn into an ion. In that case, the base will be in the water solution. So now from your original, we have a basic scheme. We'll show a little bit more how it works later, but we have a basic scheme. We have our sample. Okay, we got it from the water. We have a sample, not from the blood. We have a sample. Acid, base, and neutral is in there. We're going to turn it basic. Get a sample, turn it basic. Okay? When it's basic, the acid will turn into an ion. Get the oil, the water. The water will have the acid, and the neutral and the base will be in the oil. Okay? That's the first thing. So you separate the oil and the water. Acids are out. Bases and neutral are in there. Okay, now you have you have that stuff in the oil. What you do is remember, a base will turn to an ion when you make it acidic. Make this acidic. Make now what you have acidic. The base will turn into an ion. Then the base will get into the water. So now your base is in the water. Separate the water and the oil, and the water that you separated now has the base. From the first time you had the acid, now this water solution will have the base. What remains in the oil will be your neutral compounds. You have thereby separated acids, bases, and neutral compounds. This is what the forensic toxicologist does very often at the first step. Here's a better scheme, it's a better looking scheme. You're starting off with this, let's say in an organic solvent. Acid, base, neutral. Make it acidic. What happens? Base turns into an ion. Okay, you have let's say your organic level here, your water over here. What happens? Make it acidic. If here's your water, the water will contain the base. Remember, the base will turn into an ion in an acidic solution. So you turn it acidic, your base will be an ion, base will be in the water, base therefore goes into here. Separate the water, you now have all your bases in one container. The top layer, however, has both acid and neutral. What do? You make it basic. And acids, when you make them basic, turn into an ion. When they're an ion, they will be in the water solution. Okay? The water is on bottom, let's say the organic layer is on top. So again, you have acid and neutral, you make it basic. Acid turns into an ion. Acid will be in the water solution. You will separate them because oil and water separate easily. So your water layer will contain your acids. You have now separated the bases and the acids. Whatever is left behind in the organic layer are the neutral compounds. You now have separated your three different compounds. Your bases, your acids, and your neutral compounds. And each one of them are separate. You can analyze this one for the bases, cocaine, crack. The acids, you can analyze them for barbiturates, and the organic and the neutral ones for other things. Incidentally, lysergic acid, yeah, that's an acid. Okay, so now that you've separated them, you have a little bit less to work with in each one, so you have to do a little more specific tests. So these more specific tests, the screening tests of these acid, base, and neutral divisions, one of the first ones they do, well, it's not the first, but one of the initial ones is the immunoassay. This tests for drug-antibody interactions, like drugs will react with antibodies. We'll see a little bit about how these antibodies work. Basically, the body produces antibodies. I mean, let's say a cat, a mouse, a rat. We use rabbits mostly, but you put a drug in there, the body's going to try to fight it off, and it'll develop antibodies to cling to this drug and hopefully destroy it or to enable to drag it out so it'll be flushed out of the system. So your body, say, it finds the drug, it develops an antibody that'll stick to this drug specifically. So if you can get an antibody that sticks to this drug specifically, you mix this suspected sample with the antibody. If you see it sticking to it and clinging to it and making a cloudy solution or a darker solution, then you know it's that drug. So the thing about immunoassay, the method that's called an immunoassay, it has to do with the fact that bodies develop immune responses to drugs. So it's called an immunoassay. You test it with the immune system idea. You get the antibody for the specific antibody for the drug, and to see how it reacts. See if it reacts. If it does, then we know we have that drug. This is useful for even trace amounts of a drug, especially marijuana, because that really, it's like smoked. So there's not much gets through the lungs, from the lungs all the way into the bloodstream. That's easy to find. They're very traceable, very small amounts. So for this is a great idea to use for small amounts. Incidentally, in the organic chemistry, they know there are many ways of separating things or purifying compounds. One of the ways that's used for trace amounts is the extraction technique. That's this one, the extraction technique that we used. It's useful for trace amounts. I was dealing with trace amounts, and it wasn't easy, but hey, it had to be done, and I was able to do it, fortunately. Anyway, back to the forensics. So they do the immunoassays. They also do thin layer chromatography and gas chromatography. We mentioned these before. Thin layer chromatography is you put your spot on a paper. The different parts of it will travel upward upward on the paper due to the solvent that's put there. We can see different components. That's more or less what it's used for, to see how much is in there. We have our, let's say we have our acid level thing. So we put a spot of that on our thin layer chromatography. We'll see it separates into 3 parts. We know there's pretty much only 3 parts, 3 things that we might have to look for. So that's what thin layer chromatography is generally used for, just to find out how much there is and how many things there are in there. Gas chromatography is where, again, we've seen this before. You make it volatile. You evaporate it. Send it through a special column. Different gases will stick to it in different ways, and from the different times it'll spend sticking to this column, you can find out what the different things are. Neither one of these it tells you exactly what it is. It just separates them, or it tells you more or less what the thing is, because it's not always true that one thing will stick in exactly the same amount of time to the gas chromatography column. Only one thing will stick there and nothing else will. Sometimes 2 things stick more or less at the same place. So these are presumptive tests. They're good to tell you pretty much what to look for, but they're not conclusive. They know exactly what it is. What you do after that is you put it in the GCMS. That's a gas chromatography mass spectroscopy device. The mass spectroscopy will tell you pretty much exactly what it is.